Hello everyone, I'm Andrew Sinclair, founder and CEO of trajectorE Engineering. It's an exciting time in our industry. The world is on a journey to transition to more renewable energy, and the need for critical minerals will be higher than ever. In this series we call trajectorE Insights, we share best practices and war stories from friends and colleagues who have a history of starting new mineral processing facilities. So this is a presentation I delivered at the CIM Conference in Montreal in May of 2023. It's entitled Minimizing Emissions Intensity Through De-Risking Ramp-Up. So really discussing the critical period of a project's life cycle, which is ramp-up. It's a critical trust-building period of a project, and talking about how success in that period of the project is not only around production, but how that also correlates with emissions intensity. So we'll understand what the impact of ramp-up delays have on emissions intensity during that period. First we'll introduce what the concept of emissions intensity is. We'll explore a few scenarios. We've modeled a few scenarios that are sort of common ramp-up challenges and risks, and we'll discuss how to reduce those risks. So first, what the heck do we mean by emissions intensity? It's actually a pretty standard industry agnostic metric, which essentially measures atmospheric emissions divided by that unit of activity. So that could be widgets produced. In the case of electricity, you'll see on the slide here the Canadian electrical grid emissions intensity is trended down over the last few decades, which is excellent. As utilities transition to more renewable sources of energy. Based on 2020 data, you'll see there that the average emissions intensity for the Canadian electrical grid as a whole is 110 grams per kilowatt hour. So we'll use that in our calculations. And of course, in the mining mineral processing sector, it's tons of carbon dioxide emitted divided by the tons of the minerals produced. So as a quick calculation example here, if we take a pretty standard mine mill site with a nominal load of 60 megawatts, annual production of 50,000 tons per year, and if we use that Canadian grid, we assume this operation is connected to the grid, and so we'll carry that 110 grams per kilowatt hour. After some math, we get to an emissions intensity of 1.16. Now, of course, that assumes we're at full production, steady state. So that's essentially, barring any emission or any energy efficiency projects or whatnot, that essentially is the minimum. That's the low point of emissions intensity for an asset's life cycle. And of course, during ramp up, the characteristics of that is going to be different, and we'll get into that in a little more detail. But first, why is this important? As I said, the ramp-up period for a new asset is a very critical period, not only from an investor perspective wanting to get that return on investment and ramp up. The time value of those dollars is very high because it's early in the life cycle. But also for community stakeholders and regulators. Of course, during the project sanctioning process and permitting process, a lot of commitments are made, and the project is touted by the operator as a good project for everyone. And it's at that point, where those stakeholders are expecting to see some delivery on those promises. So certainly getting the project off on the right foot is critical for all stakeholders. And if ramp up goes well, as we'll see, that helps minimize emissions during that period, minimize emissions intensity. It also shows value for shareholders and just builds confidence and sets the project off on the right foot. Because as we've seen multiple times in the industry, if you have challenges during ramp up, it really sets a challenging tone that the operator needs to recuperate or come back from throughout the rest of the asset's life cycle. The risks with ramp up, we really categorize into one of three categories, or three buckets. There's process flow sheet risk, there's project execution risk, there's operational readiness risk, and as you can see from the stat on the screen, McNulty in his sort of seminal work in the late 90s, 45% of projects, within 3 years of startup still don't hit, full production rates. So this is a period that's fraught with risk, and we'll talk about each category and model each one. So if we go through a bit of an example and how we're going to model this during ramp up, anyone who's an electrical engineer like me, the electrical load that is associated with the project is really broken down into two components. There's the fixed load and there's variable load. So the fixed load is the electrical load that whether or not you're producing any metal or any minerals, you're going to consume that anyway. The variable load is that varies with production, and it might be easy to sit there and say, okay, well, if the variable load is the big bulk of it because it's all of the process or process equipment load. Particularly during ramp up, that's not actually the case, because if you think about, if you've been through ramp up, you think about, you may have bottlenecks at various stages of the process. So you may not be making finished product at the end, but you're still running your equipment. So if you, for instance, have a slurry tank full of slurry, just because you're not making finished product at the end doesn't mean you're shutting down the agitator, for instance. You've got to keep that, to keep the solid suspended and prevent sanding out that tank, you've got to keep that running. That's just a sort of a small example that illustrates the point. But for the purposes of our modeling, particularly during ramp up, we had some really robust discussions internally about what numbers to carry. So we carried a 40-60 fixed variable split. We could debate that, but for the purposes of the modeling, that's what we're carrying. So if we look at our first scenario, let's call this the base case. In this scenario, the process flow sheet has got mature technology, well understood. The project is delivered on time, on budget, and the operations team is ready to accept those assets and start up. And so this would generally, from what we've seen, be typical of a ramp-up curve that you'd see in most, cash flow analysis associated with a project. In this scenario, those first 50,000 tons, on a cumulative basis, which is the first, full year planned production, but the cumulative time to achieve that is 75 weeks. During that period, you see 68,500 tons of emissions, and that average emissions intensity during that period is 1.37. So again, higher than the 1.16 in the sort of minimum steady state period. But this, I think, by all accounts, would be considered a successful ramp up of a typical mineral processing operation. 39 weeks to get to 90% production. Now, we know, of course, again, anyone who's been through ramp up knows the ramp-up curve does not look perfectly like that. It probably looks a little more bumpy, like this curve. For the purposes of this analysis, we're gonna call that sort of normal ups and downs, normal friction or noise in the ramp-up curve. So these scenarios sort of are over and above that normal noise, if you will. The next scenario is really focused on process flow sheet risk. So in this particular case, the flow sheet had some new components, was sort of new technology, but really, the project had not fully de-risked that process technology by doing as extensive a test work as it probably should, and that falls into the category of a McNulty Type 3. McNulty, if you're not familiar, in his paper in the late 90s that I referenced earlier, essentially broke different mineral processing types or different mineral processing project types into 4 types, and each had different characteristics. And in this case, this falls into a McNulty Type 3. In this scenario, 90% production is actually never achieved, and unfortunately, that has been known to happen. That first 50,000 tons takes 93 weeks to achieve. The emissions intensity jumps, or the emissions, total emissions jumps up to 76,500, which is 8,000 more than the base case. And the average emissions intensity is 1.53. Again, it jumps up from their base case. The next scenario is really focused on project execution. So this risk is what we're exploring here. In this particular case, the project had some execution challenges, and if you run into delays or you're running out of capital funds to finish the project, oftentimes what happens is a rescoping of the project is done and breaking it into phases. So in this case, what we've modeled here is essentially the project's running over budget, and the project is rescoped to focus the funds on finishing the assets needed to achieve 65% production rate, which is essentially what we call phase one of the project. And then that way the operation gets up and running, can start selling product, generating some positive cash, or at least having some cash in the door that isn't coming from investors or lenders. And that helps fund the completion of phase two. So that's where you see the bump in this ramp-up curve. In this scenario, 90% production is achieved after 76 weeks. Those first 50,000 tons take 92 weeks. You see over 7,000 tons of emissions above the base case during that first 50,000 tons. And the average emission intensity is 1.53. Again, sort of similar to the last one. This one's a little more fun. This explores the operational readiness risk. And this is where, essentially the operator isn't fully ready from a personnel training perspective, from a maintenance program perspective, and so on. And you can see this is a little more up and down, not quite as smooth even as the last one with the bump in it. And so you can see as the bottlenecks shift through the process, various operational challenges arise. So at the early stages of ramp up, the front end, the crusher has some significant downtime due to lack of spares having been procured and in the warehouse. The time associated with that downtime, of course, is dependent on the lead time of those spares and where the site is located from a logistics perspective. As the bottleneck moves through, or as we start to push different circuits in the process, we see the filter presses. Maybe the operators aren't fully trained on how to run those efficiently, and so you see cloths blinding off, and so just a lot of operational issues with filter presses. I think most of us have seen that, and that takes a number of weeks to resolve itself and shift the bottleneck down the process, and then we see the thickeners. Okay, so if the thickeners are now the bottleneck in the process, maybe the operators aren't ready to operate those efficiently, or maybe don't have the experience in operating those. So drawing the thickeners down, really getting that good separation of clean overflow, high density solids underflow, they weren't able to get that mix. So you see a lot of bottleneck in the process there. And then a number of weeks in, still not at the at full capacity, but the maintenance team just has fallen so far behind, and you're seeing premature failures in equipment. The decision is made just to take a couple of weeks flat downtime to catch up on PMs and some of the overdue repairs and whatnot. So this one's a little messier than the others, but still very, I think, representative of scenarios I know that we've all lived through in our experience. So that first 50,000 tons again is 97 weeks, 10,000 more tons of emissions compared to the base case, and an average emissions intensity of 1.56. So, there's some differences among those three different types of risk, but they all result in, I would say, similar impacts, again, depending on the particulars of a particular project. So now we're going to have a little fun. If you're a Marvel fan like I am, we're going to explore a case study which is the Panther mine in Wakanda. for all you Black Panther fans. I think we could make a case this is perhaps the most famous mine in the world, fictional or not. But as you can see, you know, we've used the same metrics as sort of our scenarios to date, with the 50,000 tons per year and the 60 megawatts and the theoretical emissions intensity of 1.16. But you know, Panther is a junior miner. They haven't done this before. And in this particular case, more than one of these types of risks have reared their head. So in our scenario here for Panther, you know, the project execution plan and the project sanctioning hadn't considered operational readiness as a requirement. Didn't really realize that was a thing. And you know, the project team didn't. They had some challenges in delivering in that area of the world, and so the project ran over budget. And as a junior, they didn't have a significant, you know, reserve to tap into to fund the overage. And so essentially this is a combination of scenarios 3 and 4 where, you know, that operational readiness risk and the project execution risk got overlaid on top of one another. And I think it's important to understand those 3 categories of risk are not mutually exclusive. They can happen, more than one of them can happen. Hopefully you don't get all 3. In this case, we've modeled 2 of them. So you can see that curve's got a bit of a bump, and it's got the noise of the ups and downs that we talked about in the operational readiness scenario. So in this case, you know, to get to 90% production, it takes a full 103 weeks. That's 2 years. The first 50,000 cumulative tons takes 119 weeks to produce. You can see the emissions, the total emissions are 20,000 tons more than the base case, and that average emissions intensity jumps up to 1.77. So very, you know, significantly more than that. You know, you can see in this scenario, if from a stakeholder relations perspective, our operator was touting to the local community, you know, we're going to produce clean vibranium and our emissions intensity is, you know, only 1.16 tons of carbon dioxide per ton of vibranium produced. You know, this could be seen as a very significant, you know, erosion of that trust. So visually, you know, on this slide, we'll take a look at the graphs. It's a good pictorial or visual of the different scenarios. So that jumps out, but I think, you know, the table here can show the comparison of the various scenarios versus theoretical steady state and that sort of quote unquote perfect base case. And again, you can see, you know, once you start to layer one type of risk on top of another, you really see significant impacts to the emissions. So what to do about it? You know, and each type of risk, of course, has different mitigation measures. Process flow sheet mitigation. You know, there's a lot of content. I said when I was presenting this at the CIM conference, literally in the bookstore on the main floor, there was some great. There's a lot of great content and literature out there on how to do that. But you know, depending on you know, you don't want, as an industry, we don't want to stay stagnant and not try new technologies. But if you start to layer, for instance, new equipment and a new flow sheet together, that really significantly increases the risk from a process flow sheet perspective. So managing that from a design perspective is important. And the test work you do on the flow sheet at the various stages of the project sanctioning process should be commensurate with sort of that technology risk and you know, just to de-risk it, of course. You need to have a really strong understanding of the feed characteristics that are coming in from the mine. And of course, you know, you want to make sure you select engineering partners and that those partners are bringing team members to the table who have experience in those technologies or you know, in similar projects. When we talk about project execution risk mitigation, you know, there's again a lot of well-known literature and content out there on how to do that effectively. You know, so assessing and actively managing risk throughout the project is critical. And you know, I think we have on the slide there, avoid skipping steps in the sanctioning process. You know, I think in a perfect world, that's what you do. If in some cases, you know, based on the complexity of a project, you want to jump from, for instance, FEL 1 to FEL 3 or PEA study to feasibility study, you need to make sure that you've got, you actively measure or manage the risk associated with that. And again, the nuances of that are specific to different projects. But I think just be really purposeful and careful and do that on purpose, in a purposeful way, instead of by accident and just saying, we'll skip something without taking the right steps to mitigate it. You want to have a team that's experienced in delivering in the region. Sometimes, we're in Newfoundland and Labrador, and I haven't done work in Labrador. Sometimes I think there's been instances where project teams have come in and tried to deliver a project in a certain way in a northern climate that maybe they hadn't done before, and that if you're used to delivering projects in a warm climate, not everything is transferable. So that can be tricky. You want to make sure you've got a good, high-quality engineering design to mitigate, productivity risk in the construction phase, and you want to make sure you're keeping the project in control. So you've got a good, strong project governance process. From an operational readiness perspective, again, in our experience, many of us have worked for several years for operators and been on the operations side of ramp up. Operational readiness is just as important as the others. Sometimes gets overlooked though, I think the key thing here is don't wait until execution. When we see that, we often see owners may not have budgeted for it, and everything costs money. So you've got to have the people and a program in place ready to go as part of your execution plan to make sure that this gets done. And that needs to cover all aspects of operational readiness, as you can see from the graphic. It's not only, for instance, maintenance. It's not only, having people trained. There's a multi-dimensional approach to getting an operations team ready to run a facility and ramp it up. So you need to make sure that's covered. And start it during the study phases. You don't have to do a full-blown, start a full-blown OR program at FEL 2, but typically at FEL 2 is where we see value in at least defining some of the strategies of how you're going to maintain the facility, how you're going to run the facility, because that can have implications on the design, and you want to make sure the design and the operations philosophy are in sync. So that's an important step. And run that operational readiness program as an integrated part of the overall project instead of kind of a siloed approach. That's very important as well. And of course, hiring some of those key management positions early, at least during the early execution phase, if not during the study phases, to make sure that that voice is heard throughout. So to summarize, essentially, emissions intensity, again, because of the fixed and variable nature of the electrical load, is higher during the ramp-up period. So again, I think if operators or project teams are making commitments to community stakeholders and regulators, you need to make sure you really model that correctly and understand that. And delays in ramp-up can have significant impacts not only on production and financial metrics, but can increase obviously can increase that emissions intensity during that period. And again, that's a very critical trust-building period with your external stakeholders. And to mitigate that, of course, as we talked about, there are 3 different categories of ramp-up risk, all of which need equal time and attention to mitigate. So, if you're working on a project and getting ready for ramp-up, hopefully this adds some value and helps you mitigate those risks.